I want to solve longest common subsequence problem, which is problem number 1143 of Leetcode. You can refer to that problem and see some more discussions. And as I told before in the meetup comments section, it is actually a DP problem, dynamic programming problem. But the reason I'm selecting DP problems in the meetups is that most people are struggling with DP problems, especially writing the tabulation parts or iterative solution for DP problems. And if you are not new to my meetups, you know my procedure, you know how my approach to solve these problems. And usually I didn't see, this step-by-step in any textbook or any course, any content actually, and how I'm converting the basic brute force recursive solution to a memoization. Actually, it is, you can find that that part in courses, but converting the memoization to tabulation or iterative solution, I try to teach. Actually, I teach really straightforward mechanism, algorithm to convert really mechanically the memoization solution to tabulation. I didn't see anywhere this approach in any course, any textbook. And the reason, I want to in that way is that if you find the memoization solution, even, the recursive solution, the basic recursive solution, converting the recursive solution to memoization is really, really easy and straightforward. And also converting the memoization to tabulation also is straightforward if you follow the way I'm teaching. But if you follow, any algorithm, in other courses, you need to rephrase the problem from the beginning for the tabulation part. And usually people, when they are talking about DP problems or DP solution, their main purpose is tabulation solution or bottom-up solution. But actually, in the interviews, if you have DP problem, if you start with the basic and brute force recursive solution and convert it to the memoization, you will pass the interview, definitely. And if you have time, you can go and convert the memoization to tabulation. So the easiest way to deal with DP problems is starting with brute force solution, which is a recursive solution. And then you will see how we are converting all the steps. And if you solve, let's say 10 problems, DP problems in this way, you will be really fast in doing all 3 steps. And it is enough for interviews, on-site interviews, or even the phone interviews. And finally, after I solve this, I will summarize all the steps for the people who who joined this meetup for the first time. I'm assuming all of you guys heard about the procedure and the approach I'm solving the DP problems. So for this problem, we have 2 strings, text1 and text2. And the question is, return the length of the longest common subsequence. And first of all, you have to know what is the difference between subsequence and substring. And we know that substring is a contiguous subset of a string. But subsequence, we don't need to have really contiguous or continuous strings, but the order should be really important. For example, based on this definitions you can see here, we have original string, and we can delete some of them, some of characters. So the remaining part will be the subsequence. For example, A, B, C, D, E is our, let's say, our string, and A, C, E is a subsequence because we can have this by deleting some of the characters. For example, in this case, we can delete B and D and we will have ACE. But AEC is not subsequence because we cannot create this by deleting some of the characters. And common subsequence of two strings is a subsequence that is common to both of them. For example, let's go and do some examples. And some of my students usually ask, what is the application of these problems? And I hear lots of this kind of questions these days. And if you think you are solving some use case, useless actually, you are solving some useless problems, it's you won't have a really good feeling. I'm solving some problems, they don't have any application. That's why I put here also the applications of this longest common subsequence from the Wikipedia. And actually this is one of the classic computer science problems, and this is the basis of the data comparison programs such as deep utility and in linguistics and bioinformatics, and also in revision control systems, because in Git or in all of these softwares, we need to compare two strings with each other, and this is one of the building blocks of one of the basic algorithms of all of these systems. So it means that it is really practical, and don't think you are solving really useless problems. So let's go and switch my tablet in the tablet mode actually to be able to write down. Okay. So let's just start with a really simple example. I need something under my hand. Okay. Okay, let's start with simple example we had in the question. Let's say we have text 1, and which is A, B, C, D, E, and text 2 is A, C, E, and we want to find longest common subsequence, and we know that the answer is ACE, which is common for both of them. We will return 3. The question is returning the length of longest common subsequence. So first of all, for this kind of questions, we should think about the most basic solution without any creativity, without any optimization. We can think how we can, let's say we don't have any, we want to try all possible combinations. For this kind of questions that we want to find, for example, in some problems, the question is find all combinations, all the possible numbers, or in this case, we want to find the length of the longest common. Longest means we need to do some optimization to find the longest or smallest. And usually when you see these kind of terms, it means that you need to do, in the worst case, in the most basic solutions, you need to know all of the common subsequences to find longest one. And whenever we want to find all possible combinations, all possible solutions, it should recursive solutions should be reminded. You should be triggered in your mind. or DP. Actually, when we say DP, dynamic programming, usually I don't differentiate DP with recursive. Because all of the DP solutions can be solved using the recursive solutions. But we have some recursive solutions that we don't have any DP solution for them, right? Especially in the binary trees. So for this kind of questions, we need to do some optimizations, and we know that DP, dynamic programming, is one of the techniques to find the optimal solution. So this is the key to figure out, to detect which pattern should be used. And based on this, most probably we know that we need DP pattern. And when we have the DP pattern, we will start with the brute force solution. We don't want to dive in the iterative bottom-up tabulation solution. We want to start with brute force recursive solution. So let's start with brute force solution. And our objective is to find all common subsequences. We want to try all of the subsequences of these two guys and find the longest common subsequence of these. So I want to start with, let's say we are starting, I want to traverse two strings, right? So it means that I need two indices, one I and one J. I is traversing text 1 and J is traversing text 2. So, and the objective is to finding the common subsequence. So, and also you have to be careful. You need to length of this. You don't need to return the subsequence itself, right? If you want to return it, it will be a little more, more challenging. So, initially, I want to start with I0 and J0. I will check if they are equal. It means that these two characters can be the first character of my common subsequence, right? So, and if they are not equal, it means that they cannot make we cannot create any character in our common subsequence. So it means that for if we are in text 1 at index of I and text 2 at index of J, we have two cases for these two guys. They are equal or not equal, right? They are equal or not equal. And remember, we want to find the length of the longest subsequence, right? Common subsequence. If they are equal, and let's say I want to write my signature of my recursive function. As you can see, we need two indices, right? I and J. And also we have text 1 and text 2 as inputs. Let's say this is my function. I have text 1, text 2, I, and J, right? This is the signature of my function, my recursive function. And I know that this function should return length of longest common subsequence. Let me write the acronym of this guy. Length of longest common subsequence, right? So now I'm starting with I and J. If they are equal, so in the initial, when I have I and J, I have two cases, right? And for each I and J, they can be equal or they cannot be equal. and both of them cover all of the search space. As I said, in this kind of questions, we have an optimization problem. An optimization problem, we have a search space, and we want to search all of the possible combinations. And for I and j, let's say here 0, we have two choices. If they are equal, I will write 1 plus, right? Because right now will be a will be will be inside of my common subsequence, and I can call the function, which is text1, text2, because I calculated the length so far, which is 1, plus I'm calling my recursive function for remaining strings, right? And I will move forward I and j 1 unit forward, right? I plus 1, j plus 1. And I know that this will return length of longest common subsequence for these two strings, starting from I plus 1 and j plus 1. And I don't want to think how it will be done. I don't want to go inside of the recursive calls. But today, actually, I will do, I remember one of the sessions, one of you guys asked me, can you go all the recursion stack? And he was really interested to see how it is happening. Today, I will do that for this problem, but I strongly recommend you guys, don't do this when you are solving the problem. Think about this as a black box. This will return to me the length of longest common subsequence of these two strings, but starting I plus 1 and j plus 1, right? But let's say they are not equal. They are not equal. How can I go? How can I cover all of the options? Also, we have two cases. I can increase I 1 unit, but keep the j, because we want to check all possible subsequences, right? So will be f of text1. Usually we don't write the constant variables, but I'm writing here to make it more clear for everyone. I'm increasing I, but I'm not increasing j. So I will calculate this guy. Also, I need to calculate the other combination. I'm not increasing I, but I'm increasing j. So this will give me the length of longest common subsequence if I'm starting with I plus 1, which is b here, and j for this sub problem. And this sub problem will solve this for I from 0 if we are in the initial state, and j is pointing c. If we have this, definitely this will be our answer, right? Because we want to find longest, and definitely 1 plus this will be larger because we have already 1. But let's say if they are not equal, we will do this or this. So I will return maximum of this and this. In this case, we will say maximum of these two sub problems. So as you can see, we have 3 sub problems in the top level. And this is the most critical part of DP problems, to detect how you want to solve it. The most critical and most creative part is here. You will say, I want to do the brute force. I want to start from I0 and J0. The index at I and J can be equal or not equal, actually the value at these indices. If they are equal, I will have only 1 subproblem, which is I plus 1 and J plus 1. If they are not equal, I have 2 subproblems. I can increase I, or I can increase J, because we don't want to miss any combination. And I know that for this, this function will return to me the length of the longest length, And this also will return to me the length of the longest common subsequence. And I will return the maximum, which one is maximum will be my answer. And if this is the case, definitely I will return this because I have already one. The current character is common, and definitely my answer is here, right? In this way, actually, right now, everything is ready to write a code for brute force solution. I want to write the basic one. And if you are interested, I can go and see for you guys a recursion tree and recursion stack, and you will see how it is. Actually, I want to show you bottom up what's happening in recursive solutions. But I know most of you guys know, but I have some, in the last sessions, I had some people who asked me, can you show what's happening? Maybe it is a good practice for beginner level, people, students, or I don't know, interviewees here. So as you can see, we have, this is our top function, top signature, top function, top level. And we should check the equality, and then we will call it. And right now it is really easy to convert all of these guys to the code. And then I will talk about the base cases. Usually I don't talk about base cases at first. I write the recursion part, and after that, it is much more easier to detect the recursion, the base cases. And even at this step, you can talk about the base cases. As you can see in the function calls, only I and j are variables. First of all, you have to detect base variables, and both of them are increasing. It means that we need upper bound. We need to check the upper bound for base cases. So what is the upper bound for this problem? Any comment?
Length of the string?
Yes, for both of them, right? So it means that if I is equal to len of text1, so I have to check this in the base case, right? Because if I is length of this, it means that I traverse whole text. And if j is equal to length of text2, if you have, let's say in some problems we have I-1, right? You have to check the lower bound. If it is less than 0, or okay, if it is less than 0, you have to return something. So if these guys, I is at the end of text1, or j is equal to length of text2, what will be the our length of our longest common subsequence? Let's say I have these two texts, and my j is here, right? And I, whatever, we don't want to talk about, because I made this here, j is this, or I. It means either one of them, is finished. And let's say I is here. What is the length of common subsequence for this sub problem?
J minus 1.
No.
Whichever is smaller, minus 1.
So, the question is, we have it text 1 and text 2, right? And our index j is outside of the text. And the question is, I think this as a simple question, right? What is the length of longest common subsequence between, text 1 and text 2, starting j outside of the text 2 and I, let's say, everywhere? We don't have any common subsequence, right, for this sub problem. So it means that it should be 0. So it means that if we have these guys, we have to return 0. Actually, this problem is not really difficult to finding the, what you have to return. But in some problems, we have really challenging. I saw, people are struggling in this, finding what should they return. First of all, you have to know what is the return type of, or what is the return value of your recursive function. It returns length of longest common subsequence. So it means that you have to return a length, right? And based on these indices, you will find the condition of your base case. That case is not really difficult. And if you want to find what you should return, you have to think about the problem definition. If J is here, what is the longest length of the longest common subsequence? 0. And if, let's say, if I is here, is outside of the text, and doesn't matter what is J. So again, length of the longest common subsequence is 0 because we don't have any text actually for starting I outside of the text one. So it means that right now, actually, without before diving into the code, we also finalize the base case. The reason I'm writing first the recursion part to detect what's happening, how I'm calling my recursive functions, right? Maybe some guy, want to start from the end of the string and solve this problem. And he or she wants to decrease the i's. So my base case should be if I is equal to -1 or is less than 0. That's why if you try to write first the base cases, based on that you have to figure out your recursive parts. But because the most critical part is the recursion formulas, I strongly recommend you guys to do first the recursion part, and then based on your variables, text1 and text2 are constants, right? And the inputs that you are changing, you will find you need upper bound or lower bound. And based on that, you will find, the condition of your base case, and you should revisit the problem definition and find what's with the return value. If you don't have any question, I want to go and write the basic part because we have lots more steps for this problem. 4 steps we will have. If you don't have any question, I can go and write the code for this part. Okay, let me check the chat part. I think we don't have any. Okay, so now I want to convert this, this solution, actually, this code. Actually, this is kind of pseudocode, right? And let's go to the text mode. And I want to put it here. Styles. I have a code style. I like the font of the code style, but I think I need to a little zoom in. Make it small. Okay. So we want to define, find, actually length of longest common subsequence. Actually, find is good. Find len of longest, and we have text1 and text2 as inputs. Actually, text2. Okay. So, and as we said, we need to implement a recursive function. So we need a helper, because for a recursive solution, we need 2 more inputs. That's why we write return helper. Actually, I'm writing helper because in the interviews, because we don't want to spend a lot of time to naming, but you should try in the interviews actually to show that your naming style is really good. But helper is not really challenged. The name of your variables should be really meaningful, and it will show that. If you don't want to do that, you should mention that. In order to save time and space, I'm choosing short variables, and I know that I have to have really meaningful variables. Please, if you don't you don't want to have meaningful names, mention about it and you talk about it to show that you know this concept coding. You know what is the coding style and what should you write readable code. So text 1 and text 2, and initially index for both of them are 0, right? And let's go and define our helper. Text 1, text 2. Let's say I and J. I have a problem with this editor. When I write an I, it converts it to capital I. I set all of the settings, but it is still doing the converting for I. So let's go and write. I don't want to write the base case here first. You know, actually we talked about the base case. Let's do this right now here. If I is equal to len of text 1, or J is equal to len of text 2. It means that we traversed already all of the one of the strings, so we don't have any. The length of the longest common substring will be subsequence will be 0, and we can return 0. Let me change this to I. Okay, and this is our base case, and now it's time to check this condition, equality. So I will check if text 1 at index of I is equal to text 2 at index of J. If they are equal, we said that we have this subproblem. And we should return this actually. We can return this guy. We have to return 1 plus helper text 1, text 2, I plus 1, and J plus 1. Okay. This is the first part, and if it is not equal, we don't need to write else because we have return here, right? If it is not equal, we will be here and you don't need to write else. And we have two subproblems, right? This and this. And we need to calculate this and return the maximum of these guys. And so I will write len 1 will be equal to helper text 1, text 2, I, let's say I plus 1, J. I just moved I forward, and len 2 will be helper text 1, text 2. I don't want to move this guy, but I want to move J. Okay, so we have these guys, and we will return max of len 1 and len 2 because we want to return the length of the longest common subsequence. And this is the first solution, which is the brute force solution. And let's talk about time complexity and space complexity. And then if you have any question, I'm very happy to answer your questions for this part, because this is the, I think, the most critical part of DP problems. You have to figure out how to formulate your recursive part. It means here, actually, always we have some sub problems, and you will find at each step how many sub problems you have. In some really more complex problems, maybe you will have more layers, right? Let's say even for this one, also we have 2 other or 3 other sub problems. Only this part will be a little wider and bigger, but the general idea is this: you have to divide, or divide your search space to some sub spaces, right, or some sub problems. And don't think you are writing a recursive problem. This is the point. If you think you are writing a recursive problem, you will struggle in solving the problem. You think it is another function. You don't think it is your the recursive function. Think this is another function, and it returns the length of longest common subsequence between these 2 guys, starting this index and this index. Okay. Think. Imagine this is a function, and it returns the length. Also this and this. Write this without thinking about the base case at first. Write this part and think that this helper is another function. It is not your, you are not doing the recursive. If you think that you are doing the recursive part, you will struggle in this part. Think this is another function. It returns you the length of the longest common subsequence, starting I+1 and J+1. And in the same way, this and this. And the logic here is super easy if you think this is another function. And after you did this, go ahead and think about the base case. And the magic of the recursive solutions is in the base case. Because we go all of these guys one by one, and we have nested recursion calls. And finally, at the end, we will return 0 and then go back up and return the value. But you shouldn't dive in those recursive calls. If you think this is another function and returns the length, you can develop this part really easy. And then, based on the variables, you can figure out what should be the base case, without thinking about what's happening in all of these recursive calls. Any question, any comments? I'm trying to make it really easy, because it is really easy to get lost in DP or recursive problems. And you have to review again what this guy is returning. And based on that, you should develop your logic. Any question? If you don't have, I'm going to go to the time complexity. Okay, so what is the time complexity? Any comments?
Len of text 1 into len of text 2.
Can you repeat again? Sorry.
Is it the length of text 1 into length of text 2?
Okay, so let's say length of let's say length of text 1. Length of text 2. Let's say this is m and this is n, right? So you mean m power n, right?
M into n is what I meant.
Okay. Any other comments? So, mhm.
Yeah, I believe it will be more than m into n because
Yeah.
there are 3 recursive calls are there, right? So
Yes.
So every call we are basically, like going through both the parts. So I'm just trying to visualize.
Mhm.
So it will be like definitely in a exponential term, right?
Exactly. Exactly. It is exponential. In brute force recursive solutions, when we have more than one recursive call, definitely we have exponential. And how we can detect what is the base of the exponential? Exponential is, let's say something k power n, right? Something like this. And we need to detect what is, let me write like a power x, right? I want to write it general. And now we have to detect what is x and what is a. So in order to find a, it is really easy to find in recursive calls. Any comments? What is a here?
It will be 2.
It is 2, okay. Any other comments?
Yeah, it will be 2 actually because either the text is same or the text is not same, right? So if the text
Yes.
is same, so that will be one branch, right? And if the text is not same, then we are branching out 2, correct? So
yes.
I believe, yeah. So
Yes,
that will be
exactly.
I mean, I'm just thinking logically,
Yeah,
how the
actually, it is true. Your discussion is really true. We have 2 cases, right? And in big O, we have to find the worst case. If we consider this in the first case, we have 1 recursive call. And actually, it is not exponential, right? But in
correct.
the worst case, we have the second part, and we have 2 recursive calls. And I have a typo here. I will correct it, helper. Okay. So because we have 2 recursive calls, so it is 2. So our exponentials in a exponential base is 2 because we have something like this. At each step, we have 2 recursive calls, right?
Yep.
And also we have another case. It goes 1 by 1, right? For the first one. But which one is the worst case? These 2 guys. So A is 2. What is X? And how we can find X? X is actually the number of levels in this recursion tree. So if I want to know how many, in the worst case, how many levels, how many types I will have the recursion call.
Maybe the length of like how many characters we are going through, right?
Okay. In terms of M and N, can you say what is that?
Max
M
of
plus N.
Max of
m comma n.
Okay, one comment, one of the I've heard M plus N, and we said some of you guys said max of M and N, right? So which one actually? Which one is the worst case? We want to check what is the worst case. I don't want to really solve really fast. I think discussions are much more better.
yeah.
Okay, so which one is true? Any comments?
M plus N?
M plus N, okay. I think that's true. M plus N is actually answer. Because we want to find the worst case. And the worst case is, let's say, we have 2 strings and A, B. It is really, you can find an example that every time we call, I plus 1 and J plus 1, it means that we need to traverse whole of the text 1. In the worst case, we need to, let's say we have text 1, text 2. In the worst case, we will traverse all of the text 1 by 1, and also all of the text 2 1 by 1. It means that M plus N recursive calls we will have. in the worst case, actually assume that we don't have any case that text 1i is equal to text 2i. For example, we can have this kind of examples, you know, A, B, C, D, and Z, X, Y, T, let's say, right? If we go, all of them should go one by one, right? We don't have any equal common characters. We have to traverse both of them. Always we will be in this part, and I have to traverse all of them one by one, and also all of them one by one. And it means that we have to traverse all of them. So it means that, you know, the depth of this guy will be m plus n in the worst case. So time complexity will be 2 power m plus n. This is, you know, the way you have to discuss about the time complexity of the recursive. You know that it is a power x. Sometimes we have some other questions. We do some for loops inside of this, and you need to, for example, write n a power x. But the most critical part is finding a and x. Any comments? Any discussion regarding the m plus n?
I think it makes sense.
Okay, perfect. So, and what is the space complexity? Any comments? I think you guys should know.
Yeah, I mean, so basically there will be a call stack, right?
Yes.
So which is of course, you know, has to store somewhere in the memory to go to the next level. So that is the depth of the
depth of the tree, right?
Yeah.
It means that it is order of m plus n, right? Actually, when you have recursive function, first of all, think about, you know, as we do in all of the other problems. Do I use any data structure? As you can see here, we don't use any data structure, right? So we don't have any space complexity in terms of our, you know, data structure or anything we are using. But in recursion, you have to always talk about the stack space. And a stack space is the worst case in the depth of your recursion tree. And here it is m plus n. Usually it is equal to power of your exponential function. Usually, I'm not, you know, saying it is not a rule, but, you know, in most cases, this is true. If you find this guy, because, you know, the power of your exponential is exactly depth of your tree. And even if in some problems, if you do some data structures, you use some data structures, which is, for example, let's say m times n, and we know that order is m times n, right? But you should talk about the recursive stack space. If you have a recursive solution in the interview, please talk about the stack space. It is really important, even if it is not big O. Okay, so I think, you know, the first part is done, and now we want to go and optimize this because it is terrible, right? Exponential need to optimize, right? We need to optimize this because exponential is really yeah. So and we know that if we have brute force recursive solution, we can do the memoization, right? We can do the memoization to make it optimize. I want to show you today. Actually, I prefer to go to teach all of the steps. I don't want to dive in to the final answer. I want to show you why we can optimize this guy. to give you some insights, here we do solve lots of sub problems, right? Most probably we are solving some sub problems for several times, and we want to avoid it. Sub problems are repetitive, and we are solving them for several times. And if we save the result of any sub problem in any matrix, in a matrix, we don't need to calculate this, and we already saved this. That's why we name this technique as memoization. It means that we use a memory to keep the results of any sub problem we already calculated, and we avoid solving that sub problem. And let's go and check, do we have, for this simple example, A, B, C, D, E, and A, C. I want to go and draw the recursion tree, and we will see, do we have any repetitive sub problem or not. Okay, let's go and do this here. Actually, we have initially A, B, C, D, E, and A, C, E, right? And we know that I and J are 0 initially, right? I is pointing here and J here. They are equal, right? Because they are equal, I have only one case. Let me write a little. This side, I don't have any space. Okay. So we will start with 0, 0, and we know that for this guy, we will go. They are equal. We have to increase I and J, both of them. I plus plus and J plus plus, right? And we will have. Let me write only but I want to write only in this indices, but it will be a little difficult for you guys to track. Let me do all of them in detail. AC. So we increase I and J. So I is here, J also here. And what is the values of I and J is 1 and 1 here. And we call the recursive call for this I and J. I don't want to write the recursive call, the signature of the function, but the variables are the most important parts of the signature of the function. We start with 0, 0, and the next call will be 1 and 1, okay? And now B and C is not equal. They are not equal, so we will have 2 branches. We have 2 branches. In the first one, I want to increase I. The second one, I want to increase J. So I will have A, B, C, D, E, A, C, E, A, B, C, D, E, and A, C, E. And here we will have, I will point this guy, and J will be in its original place, and here J will go forwards. I will be in its original place, and C will go forwards, okay? So it means that here I'm increasing only I, so I will have 2 and 1. And here I'm increasing J, will be 1 and 2, okay? You shouldn't do this. I'm doing this for once because, if you are doing the recursive, definitely you can imagine that you have some repetitive sub problems and dive into memoization. I'm doing this because in the previous session, I saw some people were asking, about, the reason of all of the, the memoization, how the recursion calls are being developed. So now C and C are equal, right? The I and J are pointing to C and C. Okay, so because they are equal, we have one option only. And it means that we will increase I and increase J because they are equal. So I will have A, B, C, D, E, AC, and let's say I will be pointing D, and this will point to this guy, and I will have 3 and 2. Okay, this is one of my solved problems, and another one is here. Actually, no, sorry, we don't have any, because they are equal. We have only one solved problem here, and let's go to for this guy. They are pointing non-equal characters, so it means that we have 2 cases, 2 solved problems for this guy. And again, I++ in J++. So it means that my A, B, C, D, E, and A, C, E, A, B, C, D, E, and A, C, E. So I will point C, J will be in its without any change, but here I will point B, and J will go outside. And this is done. This is our base case. I'm not talking about, you know, the values. And actually, I want to show you this repetitive solve problems. So here we are done, and we will return the value 0, and it will go up, and you know, it will develop the final answer. So let's go and develop this guy. You know, continue this branch. And here they are not equal, so we have 2 branches. I++, J++. So I will have A, B, C, D, E, A, C, E, A, C. So if I goes forward, I will be pointing D, and J will be the same position. And here J will go outside, and I will be here. And this is also done because it is outside of the string. And here we will have, actually I didn't write here the values, will be 2 and 2, and here only will be 1 and 3. And here we will increase I, have 3 and 2. And now actually all the branches are done, and we have 2 branches, right? As you can see, both of them are same subproblems. And now in this solution, in the brute force, we do recursion for both of them. I can write this really fast, you know, all of the recursions. Only the numbers I want to write will be 4 and 2, will be 3 and 3, and then this will be done because 3 is outside of the text 2, and 4 and 2 is equal. Actually, we will have 5 and 3, and this will be done. But actually, we will have all of these guys here also. And here we will return 0, and we will come up at each of these, you know, these transitions, we do the 1 plus the previous one, right? Here, 1 plus, and here also we have 1 plus. If you refer to code, if they are equal, we return 1 plus this guy, right? And let's say we are starting here. I want to actually show you how the recursive is working. Here we will write 1 plus whole of this subproblem, right? And then again here we'll say 1 plus whole of this subproblem. And here, also here, whenever we have one arrow, because in that case we do the 1 plus, right? And here also we do 1 plus. And finally, here we return 0. 0, and also here, I'll say 1 plus also here. So 1 plus, 1 plus, 1 plus, and 1 plus. We will come out in here. Actually, the first one is not here, actually. Let's say, okay. We do 1 plus this subproblem. So we will have 1 here, 1 here, 1 here. And finally here, in this case, we will return 0 because this is the base case. 0 plus 1 will come up here, plus 1, 2, plus 1, 3, and we will return 3 because this is our, the case that's we have the maximum. And all of these guys will go up, and we will have 2, we will have, for this case, we will have 2 or 1, right? And we will return the maximum. I don't want to dive in, how it is, it is being calculated, but this is the case. We go downside, and finally we will return 0. And in one arrow recursion calls, we have 1 plus. And you can follow how for each leaf node, if you go up, you will find 1 answer, and the maximum will be 3 for this problem. And as you can see, this problem with 3 and 2 is exactly equal to this. And now we do both of them, we are calculating. So it means that we need to, for each subproblem, save the answer, and we don't need to redo the calculations. And we name this memoization. To do the memoization, we need to, the first step is to find the size of the matrix. Find size of matrix. How we can find it? You have to look at the indices, the variables in your recursive calls. We have I and j. So what is the range of I? Range of I is 0 to m minus 1. Range of j is 0 to n minus 1. So it means that I need a matrix with the size of, let's say, m times n. And that's it. I will define a matrix for this example. For example, we have m, let's say, text 1, text 2. Text 1 actually is size 5, and we have 3 here. This will be m, and this will be n. And we will put all of the results of each subproblem here. And whenever we want to calculate any subproblem, we should check this matrix. And we name this as a memo matrix. We should check this guy. If we already have calculated, we have a calculated value inside of that, we have to return it. We don't need to do the recursion calls. But if we don't have, we have to do all of the calculations and update the value inside of the memo matrix. And I want to go and change the code here we wrote. Where's the code? Actually, I did lots of, I want to copy this guy. And bring this here to change it, to see, and you will see, guys, you will see that how we are easily converting the, oh, right click is different here. Paste, okay. So let me zoom in. This is our basic recursive solution, right? And we said we need a memo matrix. And I want to change my color to red to differentiate these parts. I hope it won't change for different parts. Okay, so we need a memo, right? Memo matrix. And we said memo matrix will be a 2-dimension array. And in Python, actually, depending on your language, you know how to define a 2-dimension array. I want to put -1 initial value, and with -1, I can detect that if the value in this memo is -1, it means that we didn't calculate already the subproblem for that indices, right? For this in range, and I want to make my column, and my column is len of text 2. okay? And then I want to repeat this matrix for number of rows, which is, I will do this. I want to repeat this matrix for in range len of text 1. So actually, let me a little zoom out to have space. So actually here we have memo. Oh, let me increase the size. Okay. We have a memo with size of m times n actually. Oh, I don't know how to write it. Okay, m times n. Okay, so we define a memo and we have to pass this inside of our function. And I want to change this color to red. And we have to change, first of all of the signatures. Let me do this. And we are, whenever we are calling our recursive calls, we have to add memo. This is the first step. Please do this because usually we forget this. And if you do this, it is not really critical, but in the interviews, it shows that you are really high accuracy person, okay? And it has really impact. So we did this, right? And another step, the next step is to check if value is -1, and the value of memo at index of I and j is -1, it means that we didn't do, in that case, we have to do all of these, you know, operations. So we will do if, let me do the, again, red color. We'll say if memo at I and j is equal to -1, it means that we didn't calculate this before. Let me do all of these guys. Tab, do all of these guys, okay? We have to do all of these guys, right? And if it is, let me make it a little better. I think, you know, if I say I want to make it a little easier than this, we have two ways. I can check if it doesn't matter. Let's do. Okay, so we'll do this, right? And whenever we calculate our recursive call, you know, we calculate whenever we have return. Before returning, we have to update the calculated, the answer of the calculated subproblem. We have one return here and another return here, right? In both of them, we have to update the memo. So that's why instead of returning here, now we want to put this inside of I and j. We have to save the results. So the first step was, you know, defining and passing, updating the signatures. And the second step is adding the if condition, right? We'll say if this is equal to -1, it means that we need to do all the calculations. And we have to save memo, you know, we have to save whenever we do the calculations, okay? And then I will return here memo. Before all of the returns, you have to do saving operation. And here also, before returning, you will do you will write, let me memo I and j will be equal to max of n of n2. Let me change the color. And finally, it is better to, you can keep this in this way, but it is better to write memo. Both of them are true. Okay, so as you can see, we don't change the logic. We don't change the logic. And actually, here, I think we can make it a little easier. We don't need to do returning all of these guys. We can make it, save this only here and return, have one return at the end. But it's not really important. Both ways are true. Any comment for this part? As you can see, we do return here and we save this. If we are in this case, we will do here. And actually, let me, sorry, we have to, it is a typo here. We have to do inside of this. Okay, it should be inside of this because if it is -1, it means that we didn't calculate it. We need to calculate all of them. And in this if statement, we have to calculate it and we have to save the result in the memo and we will return it, and that's it. If it is not equal, we have to do all of these and we have to update it at the end, we have to return. And assume memo is not -1. It means that we already calculated. We won't go inside of this if statement. We just simply, we will return memo I and j. And we will avoid all of the repeated calculations. Okay, go ahead.
Yeah, so do you really need to return the memo because it is the same array, which is like once we update the value in a position, so whenever the next recursion call happens, the array is already get auto, if we are not really returning the array, right? It is just
which part you are talking about? Here, the last parts, or?
Yeah, actually both the parts. Like the first part, let's say that we calculated the value and assigned to the array and just do return without really returning the matrix, right?
Yeah. Actually, you can do this here, right? Yeah, you can do this like this, right?
Just return, right? Because
update it, right? You can do this. But if you want to do this, you need to put here else, right? Because that return was working as an else for us, right? And this is another way.
What I'm thinking, we will return actually, but we don't have to return the entire matrix, right? We'll just do the return void kind of thing.
Yeah, exactly. We don't return the entire.
Exactly. Yeah, whatever you did, correct. Yeah, correct. Yeah.
And actually, also
matrix,
you
it will keep on update.
Yeah, exactly. You can do like this. Actually, I deleted the return. But if you delete the return, you need to write else here, and at the end, it is much more cleaner. But I wanted to make it really. I didn't want to make it a little complicated for you guys. I wanted to directly convert the brute force to the memoization.
Right. Makes sense. Thank you.
Okay.
You're missing a closed square bracket in the memo initialization at the very end.
Okay, thank you very much. Yeah, thank you. That's it. Okay, I think it is right now we have the memoization. And what is the time complexity for this? Actually, for this part, you don't need to think in the interviews. You don't need to do the recursion tree. You just say, okay, I have repeated calculations. I need to add memo, and you know the memo. And some cases, actually, I don't do this. I define a dictionary, a hash map, and it is much more easier. You don't need to even define all of these stuff here. You can simply define a hash map and do that with I and j in hash map. It is easier. but it's up to you. You can do the matrix or hash map also, and hash map will be the key value will be the tuple of I and j, and the value parts will be exactly the length. Okay, so I mean that if you solve one or two problems in this way, converting the brute force to memoization can be done really mechanically. You don't need to think about it. Okay, so what is the time complexity of this part? Now we are not doing the repetitive calculations, right?
Yeah, it will be the entire matrix. It has to go through one time, right?
Yeah, exactly. We are calculating all of the cells of memo once,
Yeah,
right?
correct.
So yeah, what
M
will
into
be?
N.
Yes, exactly.
Right.
So,
if I have a 5 by 3, yeah, 15 cells will be there.
Yeah, exactly. Time complexity will be order of mn, right? M times n. Because we just, we just calculating all parts of this memo matrix. We calculate in the length as m, n. We don't do more than m times n calculations. And it is big improvement, right? Okay.
Will it be the same if you're using a dictionary instead?
Yes, you can use dictionary. It will be exactly the same, only the implementation is different. Yeah, and actually, okay. Usually I use in interviews. I was using actually the dictionary because you don't need to write all of these codes, right? You can.
Yeah, but lookup in a dictionary is O of 1, right?
Yeah, but here also O of 1, because you have index of I and j. We are not searching, right? We give index I and j.
Right. Okay.
Both of them are, but actually, whenever technically, whenever we can implement our algorithm with array or the matrix, it is better to use matrix because hash map or dictionary has some overheads. Although we have time complexity is good, but here we don't have any searching, right? We don't want to find any index. So the best solution is using the array or vector matrix, because we don't need to have the complexity in implementation of. Actually, we use hash map, but the implementation of hash map is a little is complex, more complex than the array. But for interviews, it is enough. I think you can use dictionary because working with dictionary is easier. Actually, at least defining here is much more easier. You can write only memo is equal to like this, and here actually
just star -1.
You can write memo of, let's say, I and j is equal to something, right? The key of the dictionary can be a tuple of I and j. Does it make sense?
Yeah.
You can put anything here, you can concat, the I and j as a string. It's up to you, but you can use tuple, a pair of I and j, and that's it. You can replace all of the memo I and j with this code for a dictionary, and also this line will be converted to memo of a dictionary. That's it. And instead of this guy, we have to write if I and j not in memo. Okay. We'll say if I and j is not inside of the memo, it means that we didn't calculate this before, right? Do all of these guys, and then we will add this. Does it make sense?
Yeah.
Yeah. It is only the implementation. Okay. So time complexity is order of m times n. And what is the space? Why this figure? What is the space complexity?
I believe it will be, at the worst case, we are taking the entire matrix, right? We are
Yes.
putting somewhere in the memory, so it will be m into n.
Yes, exactly. Actually, we know that m plus n is same the recursion tree, right?
Yeah.
Stack space. But because m times n is more, so space complexity will be m times n, which because of the memo. Okay.
Won't it be m times n plus m plus n? Because even though you have the memo matrix, you still have that stack trace going all the way until m plus n, right? It's only
Actually, usually we say mn, right? You can say that also we have this, right?
The maximum of the two that we are taking.
Yeah, exactly. We are putting the a maximum of these guys.
Okay, got it.
Yeah, it is much more common. Okay, so now this is we want to go to the last step, which is the tabulation. Now, as you can see, we decreased in the order of, let's say, we decrease order of 2 power m plus n to order of m times n, which is big improvements. This is brute force. This is memoization. And this is time, space. The space was m plus n, but here is space is m times n. But because this improvements in time is really, big improvements, so we prefer memoization. Now we want to go and do the tabulation. And usually when people are talking about the DP, their main purpose is tabulation or bottom up. And actually in the first step in tabulation, we will have still m times n and m times n space complexity. But so this is a step 1, step 2, step 3. But in some cases, like this problem, we can also decrease the space complexity to order of in tabulation. I will talk about it. I just, talking about this before solving the problem. In tabulation, we will use same matrix we use for memoization. And we will solve this problem, exactly this problem, with iteration method instead of recursive. It means that we will have exactly this logic, but with iterative solution, okay? So we will have exactly same time and space, but in iterative, we don't have a stack space. Actually, if we be really accurate, we can say that in tabulation, we improve a space complexity from m times n plus m plus n, as you guys said. We decrease this to m times. And we sometimes we will see that we don't need whole matrix. We need, with only 2 rows, we can calculate this. So it will be 2 times n or n. And this will be our final step, which is the step 4. We will decrease, and let's say this will be tabulation. I'm writing usually optimal, optimize in terms of space complexity. So I want to create a new page, because this one note usually when I'm writing really, I'm just extending this, but after a while it gets slower. Let me, if I can use this only one page is much more better. Copy. I don't know why the copy is not. Yeah, it is. one of the problems of, let me bring my keyboard, connect my keyboards because when you connect the keyboards, I have short keys. You can do the copy. I want to copy this to another page to convert our code to tabulation. Copy. Let's say page. Here. Okay. Let's talk about it before diving to but I will do this really mechanically. We won't think about the solution again. Because in most, textbooks I saw, people rephrasing the problem when they want to convert the memoization to tabulation. But you will see right now how we will directly convert this guy to the tabulation. So this is our step 3, and I want to convert this guy to tabulation. The first step, let me write here. First step will be step 1. We'll be defining DP matrix. So how we will define the DP matrix? It will be exactly, we will start from, okay. I erased the hash here. Let me correct this guy. I thought this was my comment actually. Copy, I erased this, okay. Okay, step 1 is defining DP matrix. So how should I define this? I have to check the memo matrix. For our example, I want to go for over memo matrix. You will start with memo matrix, and our memo matrix actually is ACE is text 1. Let's say this is text 1, text 2, and this is A, B, C, D, and E. This is our, and indices are 0, 1, 2. Let me write the indices here. Okay, so we have this is actually our memo matrix. So we will start from the memo. And the next step, check the base cases. Check the base cases and update DP matrix. And when I'm saying DP, actually in the memoization, I name memo, and here I name DP. You can, say DP for both of them. So what is the base case here? If I is equal to this or j is equal to this, return 0. It means that in this matrix, for I equal to len of text 1, which is 3, we have to put all 0. Do I have row 3? I don't have. And also for the text 2, len of text 2 is 5. I don't have column 5. I have to extend it. That's why DP matrix usually is bigger than memo matrix. I need another row here and another column here. And I know that all of these guys should be 0 based on my base cases. Okay, I'm just doing really mechanically. We have better, not better solutions that you don't need to add these row and column. But if you follow this method, it will be much more straightforward for you guys to define, to develop your tabulation solutions. So step 2, we did the step 2, and step 3. Actually, right now we want to fill out all of these guys, right? We want to calculate all of these values, like we did in memoization. In memoization, we did top down, And right now we want to go bottom up, okay? And here bottom up means we have to use base cases to update all of these guys. In order to find populating direction, you have to start, let's say I want to go with one cell. I want to calculate the value of this cell. Which cells I need to calculate this? You have to check all of your recursive calls. Find populating. So here you have to check all recursive calls. So as you can see here, in order to find the value, the subproblem I and j, I need I plus 1 and j plus 1, I plus 1. So it means that in order to find this, I need 3 values, I plus 1 and j plus 1, I plus 1 and j, and I and j plus 1. Okay, so let's go and check here. If I'm here, I plus 1 and j plus 1 is this cell. So I need this value of this cell. I plus 1 and j is this cell. Because, you know, we know that this I and this is j, right? I and j plus 1 is this. So it means that for each cell, we need all of the values from the right corner and right and bottom. It means that with having all of these values as base cases, I can calculate this guy. And then this guy, because I have all the values. So it means that I can do in this way, populate in this way. And if I have these rows, I can populate this way and this way. And my final answer will be the value of 0 and 0. We find the populating direction. So what will be my for loop or populating directions? I can write based on these arrows I wrote here. So J will go from n minus 1, actually, n minus 1 to 0, right? N minus 1 to 0. And I should go from m minus 1 to 0. So now we know the populating directions. And the last step is converting all recursive calls to DP formulas. So how we'll do that? Let's say I want to calculate, you know, we have here also, let me do the red color. We have a recursion call here, here, and here. We have to convert all of these guys to DP formulas. How we will do that? Let me convert this to the DP formula. I will write DP of I and j is equal to 1 plus, instead of writing helper, you will write DP. DP of only just variables. You don't need to text, and because they are constants, right? We have them. So you will write, will be I plus 1 and j plus 1, right? And for these guys, we just, you know, replace this line with this line. And for the other one, we'll write len 1 will be equal to dp of I plus 1 and j. Len 2 will be dp of I and j plus 1. And that's it. At the end, we will return dp of, you know, 0 and 0. And also here, we have to convert because it is memo. Whenever you have memo, you have to write dp. So you will write dp of I and j is equal to max of len1 and len2. And that's it. Right now, you know how to change the body of your code, which is here. This will be converted to this guy. Instead of doing all the recursive calls, we have DP formulas. And on the top, we have to define our DP matrix and update our DP matrix based on our base cases. And that's it. And finally, we will return DP of 0 and 0. Based on the directions, you will figure out which cell will have your final answer, because we want to traverse all of the strings. The reason I'm doing this, because I don't want to rethink about this problem. If you see the answers in the textbooks everywhere, they start from 0 and 0 and populate and find the answer in the final cell. But you need to rephrase all of the equations, and it is really struggling. Maybe you will struggle in that way, but in this way, you just convert mechanically the base cases to the initial values and all of these. It is really mechanically, and you don't need to think about that. So let me write a code for this part. And I think today's, maybe we will need a little more time, maybe 2 minutes, but it will be done in 8:10 actually. Okay, so now I want to do all of them, convert all of them, these guys to the to a code. Let me, can I select this guy? Yes, copy. And let's go here, paste. Okay, now we want to convert this. We don't need the first one. Actually, because I want to work on the second part. Actually, I need this guy. So I want to write my function, which is, let me do this. I don't need the recursive call, right? I don't need this one. And also this comment, let's get rid of this comment. And in the tabulation, actually, this is our signature, right? Let me write also at the end, tabulation. And, but as I said, we need one more column and one more row, right? We talked about it in our, actually we said we need one more column, and because of the base cases. So I did that here. So, and I don't need this guy. So, and I prefer to change this to DP. And initially we wanna have 0 for all of them. I wanna make life a little easier. I wanna make this 0 because we wanna make the last row and last column 0. And initially, you know, if you put 0, they are automatically 0. And all of the other cells will be calculated. And initial value is not important for them. They are 0, and we can put any other values, okay? So, but with the first line, we put 0 in the last row and last column. And it means that we did this base case. With one line, we did also this guy and converted to the, put all of the data order. And actually, we don't need this guy. But our, actually, this is our, the body of our, you know, exactly the body of our tabulation. I don't want to change it. But as I said, I will write, instead of memo, I will write DP. DP of j will be 1 plus, and instead of this, I will write DP of I plus 1 n we are converting okay, that's it. We do for this part, and also for the next parts, the else part, we will do this guy will be dp of I plus 1 and j, and also let me do all of these guys. dp of I and j plus 1. Actually, in order to make this a little better, we don't need to put them because they're already short. I want to do this because we want to calculate the maximum of these guys, right? Instead of doing all of these guys, okay, I will put here in len of this, len 2 is exactly this. So let's make this better, shorter code. And this guy will be dp. Actually, as you can see, I don't want it, I'm not doing really a special thing. I just converting mechanically everything to dp formulas. We talked about this. And now I have to put all of these calculations inside my for loops, which we found here in step 3, populating direction. Actually, we want to populate whole matrix, and how we will update based on these formulas we already have. Now it's time to do the population. Actually, we did, already. We have the code here, right? I will go m-1 to 0, and that's it. We have the for loops. Just convert those guys to the code. I in range will be len of text 1 minus 1, because we want to start from the, if you see here, this is this column is len of this minus 1, right? And len is minus 1 until the stop point is -1, and we want to go to the opposite direction. And I think you guys know that in Python, the end range is not inclusive. It means it will go until 0. -1 is not inclusive, and -1 means the direction. We go in the opposite direction, the decreasing direction. Let me change this also to I. Okay. And another one is for j in range len of text 2 -1 -1 and -1, and all of these guys will be inside of these two for loops, and that's it. And at the end, but we have to return 0 and 0. Okay, and actually right now we have, yeah, it's done. This is the tabulation. We just converted really in a mechanical way the memoization to tabulation. This part is exactly the conversion of the recursive calls to dp formulas, and we found the populating directions based on how we need, for I and j, I need I plus 1, I plus j plus 1. And based on these recursive calls, we can detect which direction is correct. And that's it. And here also the initial value is really important. And we did that. And actually here in this code, we do all the operations we did here, but only this is the recursive, and exactly we converted the recursive to iterative solution. And this is exactly same time complexity, m times n. And let's say, let's have to write here. We have mn is time, and also mn is space. time, and this is a space. Okay, so we have both of them. So, but if you look at the code in how we are developing, let me bring the matrix. Do I need whole matrix? In order to populate this row, I just need the next row. And when I want to populate this guy, I just need the next row, right? It means that with 2 rows, I can do the tabulation parts. So I don't need to have m times n space complexity. It can be 2 times n, which is, in terms of big O, it is order of n. We just need to decrease the number of rows from m to 2. How we can do that? I want to do this really simply here without, again, rethinking about it. It can be done really fast. So here, let's copy this. I don't want to, because I wanna share all of these guys. I'm gonna copy and paste to have the original one. Will be more readable. And so I named this as tabulation and optimized. Okay. So in this case, I just need to change the number of rows. My number of rows will be 2. I don't need that kind of all rows, right? And let me change the color. The red color is not really, yeah, I have better red here. Okay, so it will be 2. Actually, we have to populate. We don't need to change the populating parts. I and j should iterate exactly like the original, the basic, original in the tabulation. But when I want to access my DP, I shouldn't access I plus 1, because I right now can be 0 or 1, right? Because we have 2 rows. The range of I actually, I is 0 or 1. So, but I actually should traverse whole string, right? I shouldn't change this. I should traverse whole string. I shouldn't change my for loops. But whenever I want to access my DP matrix, I have to modify my I. How can I do this? I have to, whenever I have I have to write I modulo 2. And I will automatically will change between 2 rows. Let's say I have something like this. I will start with 0. I will start with 0 and I will calculate the next row. And based on this, I will calculate this. And then, it will be done, one by one in 2 rows. And how you can do this, actually, I didn't have enough time to explain it more in detail, but it is really simple to implement this guy. Whenever, you shouldn't change the index of texts because it should traverse whole text. Only change the index of DP parts. And actually here, let's say the text mode. Whenever you have I, only for I parts, right? You will write I modulo 2. And same here, whenever you have DP, because we change this, right? Modulo 2. Let me make this light. Okay. And also here, you will have I modulo 2. And also here, modulo 2. Only the DP parts, because we changed the size of the DP matrix. We didn't change any other data structure, right? And here also you will have modulo 2. You don't need to change the J because we didn't change the number of columns. And that's it. And finally, you will return DP 0 and 0. You can trace the code for this, so you will see that again. Always, we will have the answer will be at DP of 0 and 0. I'm trying, you know. Actually, I'm now it's done, and all the steps I wanted to teach today, and you will see that now this is exactly the same logic, but we decrease this guy. Actually, time is same because we do the for loops here. This is order of m times n, but we use only 2 times n, the size of the matrix. So the space will be order of n. And this is the most optimal solution. And if you wanted to find this answer, actually, this solution at first, it is really difficult. But maybe you will think, how can I find this guy in the interview? How, if I want to do all these steps, I won't have enough time. But actually, the point is, if you start with the recursive solution and then convert it to memoization, usually interviewers say it is enough. But actually, especially for this problem, if you solve some problems like this, after you find the recursive solution, definitely immediately you can see the memoization. And if you see the memoization, as you can see, the tabulation also is not a challenge. And based on the population directions, you can immediately detect that you can decrease the space complexity or not. And I remember in one of the interviews I had exactly this kind of something similar to this problem. I solved brute force. I solved the memoization. I said I can do the tabulation, and I thought about the optimization that I can do in the tabulation part. I said I can also decrease the space complexity from m times n to n. And the interviewer said it is enough, and it shows that you know all the steps. But you have to solve some problems in this way, and I think then even in 20 minutes you can do all of these guys if you practice a little more.
Could you explain a little more why it became 2 rows? I didn't quite get.
Okay. Did you get the tabulation part, right? And
yeah, I got that. Just
okay.
to reduce it to n instead of mn.
Your question is about the implementation or the whole logic for 2 rows?
The logic for decreasing it to 2.
Okay. As you can see, we have these values, right? And in order to calculate all of these rows, these values, only I need the next row values, right?
Right. You just need I plus 1 and j plus 1.
Exactly. And also, maybe I need this one, but it is always 0.
Right.
It is always 0, right? And if I go, and based on this, I can calculate the next row. It means that if I do like, ping pong, right? We say, like ping pong slide. And you can start with 1 row and calculate the next row based on this one. And then based on this, you can calculate the next row, but you are using only 2 rows.
Right. So you still need all the columns, but not all the rows.
Yes. Yeah, exactly.
Got it.
Yeah, exactly. And actually, we could do also in this way. We could, let's say, if our population was in this way, right? Also, we could do in this way.
Yeah.
And it is good discussion that you say, if m is greater than n, I can make my tabulation as order of minimum of m and n, right? Which one is
that
minimum?
makes sense.
We can do based on that, yeah. But converting is really pretty easy. As you can see, only I will be I modulo 2. That's it.
Yeah, so one thing, Wahid, right? Like you started from the reverse direction, right?
Yeah.
Like from the end of the string. So
Yeah.
yeah, and in some of the tabulation, like they started from the upper left corner rather than
Yeah.
right bottom
Actually,
corner, right? So
yeah, actually, in the textbooks, in courses, all of them are starting from the beginning. Right?
Yeah, left top.
Yeah, exactly. But that's my point actually in teaching the the tabulation. If you want to do that, you have to rethink about the problem and what is the meaning of index. The meaning of index will be changed if you want to start from the beginning, and you have to think about rephrase the problem for yourself. It is kind of solving a new problem. But if you go if you convert your memoization exactly to the tabulation, your answer will be always in the opposite direction. But converting memoization to tabulation will be really easy and straightforward.
Okay.
I have a question. This is very similar, seems to me, like the edit distance problem. But one thing, if you save the dynamic programming matrix, you can actually find a path where you find the edit distance. Can you do a similar thing here and reconstruct the actual string that's the
edit distance, actually it is also DP problem, and you can the same operations for that. Yeah, you can use this approach also for solving that one. Maybe in the next sessions I can solve also that problem.
Yeah, but I mean you could use this to, I guess, find the characters that are actually the subsequence.
Yeah. Actually, this approach, this is only the reason I'm using this way in the opposite way, because you can mechanically convert memoization to tabulation. You don't need to think about it.
Yeah, no, that makes a lot of sense.
That's actually, and for that problem also, yeah, we can do. I applied for all of the DP problems this method. It is much more easier for me, at least. Yeah.
Yeah, I was just about to ask if this can be a generic approach to all of the DP problems.
Yeah. Your question is, can we use this as a general approach for all DP problems, right?
Yes,
exactly. You can do that. And I strongly recommend to in interviews start with brute force, convert to memoization. If you have time, you will do the tabulation, and if you don't have time, you can talk about it. I can convert this to the tabulation, and then I can optimize the space complexity in this way, and it is enough for interview, even for on-site interviews.
Okay,
but
got it.
if you want to start with tabulation solution, it is actually binary. Like maybe you can't figure out this directly, but most cases I saw my students, they cannot do that. It is you have to solve lots of problems to be able to do that. But formulating the recursion is much more, I think, straightforward.
Yeah, I agree. It's much easier to come up with a recursion itself, because it becomes like a brute force, and then you apply memoization to it, and converting that to iterative was a big problem, but I think this works. So this is very helpful.
Exactly. He can do this method, and after you solve some problems with this method, you can do all of them, automatically in your mind. Maybe you can write, directly the tabulation solution. But I think in the interviews, I don't recommend to do that, because it is a little risky. Go ahead step by step. It is much more better.
Yeah, I think you have to kind of get used to it.
Yes, yeah, exactly.